For this section of the notes, we're going to look at some vocabulary and define some of the basic things that waves can do. Again, you are going to have labs during class so that you can see these wave motions in action. So first, we're going to talk about reflection. This is the turning back of waves due to an abrupt change in the medium. So you want to think almost like a rebound. Something is going to come in, hit a hard surface, and then bounce back. When we talk about the law of reflection and the way that your wave would bounce once it hits that hard surface that changes the medium, we're going to look at two different angles. One is called the angle of incidence, and that would be like the initial angle. And then the second one would be the angle of reflection, which is the angle at which it reflects or bounces back. Now, what we need to do is measure from this thing called the normal line. And what the normal line is an imaginary line that's perpendicular to our surface. We always measure our angles outward from the normal line because you may not always have a flat surface. It might be curved or it might be jagged, but if we look at a normal line that's perpendicular to the surface, this will always give us a really good reference point. So the law of reflection is going to tell us that when we measure from this normal line, our angle of incidence will equal the angle of reflection, and this is true for any type of wave. For this slide, I also have a little barrier. So if we look at some longitudinal waves that are being pushed, they are traveling in this direction, which would be the incident velocity that's coming through. When they bounce and reflect off of that barrier, you'll see that if we were to draw a normal line, that angle of incidence would equal the angle of reflection. Now for these two things over here, I do have some animations that I will show you in class. Our next term is called refraction, and this is the bending of waves as they pass from one medium to another. So in this case, we have a barrier that separates two different materials. So in this case, when we have refraction, it's not a solid surface that would cause the wave to bounce back, but rather a surface that can allow that wave to continue traveling, but it's going to throw it off course a little bit. So the wave is going to change direction at the boundary between your two different media. Sometimes you'll see this called the bent stick phenomenon. So I put a couple of pictures here for you. If you've ever tried to look at something underwater, it looks a little distorted, and refraction is that reason. Now for us, we aren't going to get into the math necessarily on figuring out how much something will refract, but I do want you to be aware that the angle of refraction can either get larger, or depending on the density of the medium, that angle of refraction can get smaller. So it just depends if you're going from more dense to less dense or vice versa, if your wave will travel kind of outward or if it'll bend more inward. For right now, you just need to know that refraction refers to this bending or changing of direction of the wave. So this is just another example for you, so you can take a moment and kind of examine the pictures and get a couple of more ideas about refraction. And yay, physics is fun! Our next vocabulary term is diffraction. So you'll probably notice these words do sound really similar, so you're going to have to pay close attention to the detail. Reflection, refraction, and diffraction. So this third one, diffraction, is the bending of a wave around and behind the edge of a barrier. So you've got some sort of obstacle that's in the way. So I have an example. These represent little water waves, so crest coming through, and they're trying to travel in this direction, but a barrier has been placed in the way. So only part of the waves can get through. Well, when this happens and you have a solid barrier, as the wave goes through to the other side, it's going to bend around and behind it, and we would see that the waves take on a circular pattern in this case. The next thing we're going to do is called superposition. I went ahead and included the definition for you. It's right here. The displacement of a medium caused by two or more waves is the algebraic sum of the displacements caused by the individual waves. Simply put, this means add the amplitudes of waves together. That's all superposition is. So we're just going to add the amplitudes of each of our waves. So I did give you an example. we are going to have wave number 1, and you want to label its 0 location, and then wave number 2, and we're going to label its 0 location. So then we can look and see if our amplitude is going to be positive or negative in order to combine those to get our third wave. So what superposition does is I'm going to add wave number 1 plus wave number 2 and come up with my resulting wave. So that process of adding the amplitudes together is our superposition. So we do want to draw a 0 line so that we can add these accurately with a good reference point. So I'd put a little note here that we're going to add each section individually. So what I've done is put a dotted line at the places where either wave has changed its direction. To make things simple, I'm going to say that anytime my wave has a positive amplitude, that went up a height of +1, and if it has a negative amplitude, it has a height of -1. So adding these two together, wave number 1 in this first section has an amplitude of +1, wave number 2 has an amplitude of 0, so that gives me a total of +1. So I'm going to simply move my wave and draw it up and over with a height or amplitude of +1. Now we're just going to keep going. +1 still is the amplitude of my first wave. Now my second wave also has an amplitude of +1. This gives me a total of +2. Since I've already moved my wave up from that amplitude of 1, I only need to go up one more step so that I get a total amplitude of +2 from that equilibrium line. Next, my first wave went back down to 0. My second wave stayed at a +1 amplitude. So if I add 0 and +1, I'm going to get +1. So I want to drop this wave back down and make that amplitude even with the amplitude I had earlier at +1. Now both amplitudes for each of my two waves I'm adding together are 0. So I'm going to drop my wave back down, and it should be even with my 0 line because there's no amplitude. When you add 0 and 0, you get 0. So I know this seems pretty simple. Go ahead and try that last part and come back and see if you got it correctly. I hope you got a shape that looks something like this. And some of your free response questions will probably give you waves that look like this and ask you to combine them. So you'll need to be able to draw a resulting wave when you superimpose two waves together. Next, we have interference, which is the result of the superposition of two or more waves. There are two types of interference. The first one is constructive, and that means the wave displacements or amplitudes are in the same direction. So remember, the displacement is referring to the amplitude. So if I were to superimpose my blue wave with my purple wave, both amplitudes are in the positive direction for the first part, and the amplitudes are both in the negative direction for the second part. So if I were to draw those, I would combine them and get a wave with a really tall amplitude for both halves. The other type of interference is destructive interference, and that's when my amplitudes or displacements are in opposite directions. So for example, my blue wave is positive and then negative, and then my purple wave is the opposite. So if I were to add those two together, we see that they happen to cancel each other out, and I wouldn't end up with a wave at all. Now, for destructive interference, the waves don't have to completely cancel like our example does here. They just have to be in opposite directions, even if one was taller than the other. So for example, if I look at my amplitudes, the amplitude of the red wave is obviously larger than the amplitude of the blue wave, but they are still in opposite directions. So one's positive while the other one is negative. This would count as destructive interference, even though they don't cancel each other out completely. So this is another example of a picture for you. You can think of constructive interference when the crests meet of a wave or the troughs of a wave meet, and then destructive interference would be when you have a crest and a trough combined. And then this is how they result in terms of their amplitudes. The last thing we're going to cover in this section will be standing waves. I didn't leave you a specific place for a definition, but you might want to go ahead and write this down. So take a moment and go ahead and write down this description of a standing wave. So in order for a standing wave to occur, you need two identical waves that are traveling toward each other. We are going to do a lab that's just about standing waves, so you'll be able to see this in person. It's kind of a little difficult to imagine and visualize, so just for right now, get the vocabulary under your belt, and then we'll talk about it more in class so you can actually see the waves. But remember that standing waves are going to occur if you have identical waves that travel in opposite directions. So for example, I have this red wave. It's going to be traveling in that direction, and my blue wave would be traveling in the opposite direction. Well, if I keep sending those pulses down, so if I create a wave train for both of those, what it's going to look like is you'll get a wave that looks almost as though it's still, and it'll look as though these little spots in between create a blur to your eye because they're moving so fast up and down that you're going to get these little pockets, or sometimes they're called little footballs for their shape, and it'll look like the wave is vibrating so fast it's just a blur, but you are going to have a defined shape on the top and bottom. As for labeling the parts of a standing wave, we have what's called a node, and that's the point in the medium that's undisturbed at all times. So there'll be parts, even though it looks like it's vibrating here, there are definitely going to be sections that don't move at all. So these are perfectly still because you've got complete destructive interference, so there's no amplitude whatsoever, and that is what's called a node. Now the opposite to that is an antinode, and that's the point with maximum displacement. So for our little part that's vibrating, the top and bottom, that's where your antinode will be for each of the middle parts of these little footballs or pockets. And this is because of constructive interference. So this is where my amplitudes are combined to be the most. And lastly, I've got a couple of questions just to review if you can label nodes and antinodes and constructive or destructive interference. In this first picture, you're asked to see how many nodes there are. So you want to look at each point that's undisturbed. So the two ends, and then every point in the middle that's along that equilibrium line. You should come up with a total of 9 nodes for this particular wave. Had I asked you about the antinodes, you would be looking at the points where the waves are the tallest, either in the positive or negative direction. You don't count both of them, it's one or the other, so all positive or all negative. But it's the part with the maximum amplitude. You can think amplitude and antinode both start with A, and you should see that there are 8 antinodes. And this pattern for nodes and antinodes and how they're related, there will always be one more node than antinode. That's something that's important. So no matter what your standing wave looks like, there will always be one more node than antinode for that wave. Now for our other question, of all the labeled points, where is destructive interference occurring? I hope you remember that destructive interference is where the nodes are. So out of the choices that were given and the points that are labeled, you should get an answer of points B, C, and D. That's it. Remember, we are going to do several labs that have to do with waves, so you are going to get hands-on experience and actually get to see and feel these different wave behaviors. Thank you for listening, and next time we will be talking about sound waves.